Hello, everyone. Today is April 22nd, 2022. Welcome to another Earth Day. And on this special day, I have a special guest. Most of the time, when we have this It Depends podcast, we talk about a product. But today, I am happy to have Jordan Tigani join us. He's a good friend of mine, known each other for many years. Most of you need no introduction to Jordan. He's the person who gave us Google BigQuery. And then he's had an illustrious career. Now, Jordan is experimenting, thinking about what are some of the trends and what are some of the needs of data and analytics space. And he has joined us to regale us with a peek into his mind. So sorry, Jordan, I think Earth's Day, too much coffee. It's early morning has gotten to me, but please introduce yourself.
Thank you so much, Sanjeev. Really excited to chat with you. Always look forward to having a conversation and a window into how your brain works. And I love to talk about databases and analytics. My background. I mean, you mentioned I was one of the people that helped create BigQuery. I wouldn't say I'm the person who brought you BigQuery, but I certainly helped it had a small piece of helping it on its way. From kind of the early days in the I think it was like 2009 when we sat around a dining room table and tried to figure out what it was we were going to build. And we had, at Google, had all these amazing tools, and we could really sort of stand on the shoulders of giants. And a lot of the Google Cloud turned into, came from productionization of things that had been kind of in the works a long time in Google. But I was fortunate enough to sort of help see the BigQuery from zero to I'm not supposed to say how much it made, but it was it was pushing $1 billion in ARR by the time I left, and got a chance to be in some leadership roles on both the product and engineering side. More recently, I'd been at Single Store running product and engineering. Kind of my background as an engineer, and so my brain works like an engineer, and I love to geek out and think about technology. But then when I switched to product, it was sort of like a whole new world had opened up. It's like, hey, wow, the world is not just about who builds the best technology. It's about like, there's so much more to actually building a great product than tech. And so once you've sort of seen, it's like almost like the world is in different colors. And once you've seen those colors, it's hard to go back and say, I'm just going to do engineering. And so Single Store, which was then MemSQL, kind of gave me the chance to lead both the engineering and product side, and really wear both hats. But one of the things that I guess I sort of realized is that taking something and growing it is exciting, and it's certainly rewarding and has its own set of challenges. I think I really want to get back to sort of building something and starting at the ground up in the creation process, because that's sort of what really excites me. So now I've been I've got something that I'm working on, not ready to talk about it yet, but should be pretty exciting, and maybe I can sort of give some hints about at least the types of problems that are interesting and the types of problems that I hope to solve.
So Jordan, by the way, congratulations on getting back into the fray and thinking about your next venture. This call is completely unscripted, so we are going to play it by the ear. You started BigQuery, you were part of the team that founded BigQuery in 2009. The Snowflake came into existence, came off its age a bit later, and you've been in Single Store, where you got to see the sort of the hybrid single database convergence of operational and analytical needs. So with this kind of background, if you were to build a new product, will it be analytical, operational, a combination, and what are some of the lessons that you've learned that you'd like to do different?
Yeah, it's interesting you mentioned this sort of Snowflake started a bit later. I'll take a second to kind of take a little dig at that, because I know you like to be provocative. But one of the things that was always frustrating at in the BigQuery team is when Snowflake would get credit for inventing something. It was like, wait, we've been doing this for years, and most likely we hadn't been marketing it or promoting it effectively. It's sort of like it used to be when so I'm a Google fanboy, and I kind of root everything in Google. But when Google or Android would come out with a feature, and then Android would come out with the same feature later on, and everybody would be like, "Oh, this is so amazing that they invented this." And Android people are like, "No, wait, we have been doing this for a long time." But anyway, in BigQuery versus Snowflake, things like separation of storage and compute, and I think separation of storage and compute, I think had been pioneered. I think everything in databases, like somebody in the 70s or 80s has done it, but certainly in the cloud, I think BigQuery was the first separation of storage and compute, data analytics system. Now that's sort of standard. Also, data sharing. This was something that people didn't realize that you could do. Was just one of the things actually that got excited. It was exciting to me about at BigQuery, and one of the sort of the founding things that we wanted to do was having this global data namespace that I think people don't always realize how powerful that is, but just every piece of data has one single name, and that way you can you can give access to it basically by sharing that access, and you can kind of see how you don't have to worry about, okay, well, where is the data, what silo is it locked in. It's just sort of it's all there. You're asking what some of the problems that I would like to solve. I think there's a couple of things that I've seen that people don't always realize. And I think I think it was Paul Graham that said something about the places where there's opportunity is where you believe something strongly that is different than what everybody else believes. Because if you just believe what everybody else is believing, and you're you're going to just sort of pile on to kind of whatever the hot thing is, and the hot thing goes over somewhere else, and you go end up chasing that. And so I've been thinking, what are the things that where my experience is different than has led me to different conclusions than perhaps the sort of the mass of the analytical folks are. And I can talk about a couple of those. So one of those is that I think big data. So most people don't actually need big data, and I think this has been apparent for a long time, since the days of Hadoop, where people would start using Hadoop, and most of the things that people use Hadoop for, they didn't actually need Hadoop for. The only thing they were doing was slowing down what they were trying to do and make it harder by several orders of magnitude. You're like, oh, but it's going to scale, whatever. But it's you never get around to the scaling part, because you're so worried, you're so spending so much time wrestling with the technology. So one of the things that I did when I was at BigQuery was I did a lot of analytics over kind of how BigQuery was being used. And first of all, while there were certainly separation of storage and compute, which I think is a great thing to have, and a key thing to have, let people have really, really large data sets. And so there certainly was, cases where people had petabytes, even hundreds of petabytes of data. But the thing is, the actual working set of that was much smaller. I mean, most of the time, you had your 10 years of logs, and most of that sits there pretty static. Maybe you query it, every few days or weeks. But the hot data, the data that you're actually accessing, is a tiny fraction of that. And so the median size that we saw was less than 100 gigabytes.
Oh, wow.
Of sort of your active data. We called it sort of the active data warehouse side, and we use it actually to sort of help match up BigQuery versus Snowflake, because BigQuery's model with slots and this sort of massive multi-tenant system was really hard to kind of say, well, this is roughly equivalent to this other system over here. And so we kind of use the sort of the data, the data warehouse size, to say, okay, this could be roughly equivalent to some other, whether it's Snowflake or Redshift or Synapse, to try to do some little bit of comparative analysis. But many people had very small data warehouse sizes. And I think the other thing is in the old school where you had, your database was this giant box. It was sort of this fixed box that everybody had to share. And kind of the newer, one of the things that cloud lets you do is you can basically have multiple different compute instances, and each of those can be a lot smaller. For example, like you might have, I think that's one of the things actually I think is really, Snowflake did really well. As I said, basically, if you have two different teams, each one of those can have their own Snowflake instance. Each one of those can spin it up when they're using it and spin it down when they're not using it. You can have an ingestion, a separate ingestion, and you size that for what you're doing. But the thing is, when you have, instead of one giant, let's say it's a Teradata instance, but you have a lot of smaller ones that have separation of storage and compute and can all share the same data, then those sizes actually that you need are a lot smaller. And so I think one of the sort of the interesting things is just that I think the data sizes and the compute sizes are not as big as people believe them to be. And and I think this is something that people haven't necessarily internalized yet, because for example, if you remember the sort of the Snowflake versus Snowflake versus Databricks kind of benchmarking war last, right. I guess it was the fall. And you think what you want about that. It was sort of fun to watch from the sidelines. But the thing that kind of jumped out at me and kind of I thought was the thing that I thought was absurd about it was the data sizes they were using were the 30 terabyte benchmarking scale. So like 30 terabyte, and from my experience in BigQuery, only the very, very largest enterprise customers had data at that scale and ran queries that actually kind of use data at that scale. And even those customers, they were much less latency sensitive. It's sort of like the times when you're scanning tens of terabytes is really kind of when you're building reports, you're doing something overnight. You're okay with sort of a very, very batch system. As a one of the things that I did when I took over product management in BigQuery was I de-emphasized our focus on scaling up. Like we certainly in BigQuery, we love to talk about how much we can scale. And I used to, get on stage and run a query over a petabyte and show how you could do it in only a couple of seconds. But instead of focusing on, the things that happen, when data is tens of terabytes, because, things do happen that are different at that scale. You have to, worry about, spilling to disk. You have to worry about, just, a lot of, certain things become much harder at that scale. I had people focus actually on the much smaller data sizes, the TPC, 1 gigabyte, 10 gigabytes, 100 gigabytes, because that was a lot closer to what customers were actually doing. Like 90% of the queries that were, so I looked at the customers that actually were between 1,000 are spending $1,000 and $10,000 a month, which is still pretty hefty customers, but that was sort of like a pretty sweet spot for these are serious analytics customers. There's they're not just kind of the dilettantes that are storing a couple megabytes or gigabytes and querying it every once in a while, but these are people that are really using analytics. 90% of their queries were under 100 megabytes, really actually kind of small. So I think that the rise of everybody kind of has, had been trained by the big data. How are you going to deal with your big data? And I think one of the interesting challenges is going to be, how do you deal with your small data, or, how do you make small data work really well? And how do you focus on just making that really, really seamless? Because, yes, you can do the giant things. And I think with the systems that we have now, you can make it so that, whatever scale you have will work. But how do you make it really spectacular and simple to use smaller data?
So Jordan, this is quite unique hearing you say this, because we've been sort of tuned to think about bigger the better, petabytes. In fact, petabytes is not even that cool anymore. It's exabytes that people are talking about, right? So you are giving this practical example that the actual working set is much smaller. And what you're saying is that we've kind of neglected optimizing the small working set. Instead, we focused on these highly distributed scale out. And when we do scale out, we being distributed, we have to think about all the isolation levels and high availability, all of that. So are you proposing that if the working set is small, then we could stick to single nodes maybe and scale up?
So that's a very good, very provocative question. I think absolutely. So, in the past, when I've sort of talked about, what you could do in single node, people are like, oh no, well, you can never be taken seriously as a database if you're not distributed, if you're not scale out. And I think that's kind of, there was this, I think when Google published the MapReduce paper and the big table paper and some of those, like, basically taking old things and refashioning them as distributed systems. I think it broke people's brains and just says like, okay, well, the old way to do things is scale up and the new way is scale out. And certainly there's a lot of really, really nice properties of a scale out system in terms of like self-healing and availability and reliability and being able to build it from, less expensive components. So everybody's been focusing on these scale out systems, these distributed systems. But in the meantime, because the MapReduce paper came out in 2003, 2004. In the meantime, the physical sizes of servers have gotten much larger. I mean, on AWS, you could spin up a machine that has 24 terabytes of RAM and 440 cores. Like that's a pretty, like, I don't know that there's many workloads that are not able to be handled by that. And if you also think about, some of the, NVMe, Optane, type things that can really give you, effectively, if not directly scale your main memory, give you kind of really, really fast access to larger storage sizes. From
how big can we go?
I don't know. I don't know how big we can go, but I think it's a very interesting question, and I feel like the you like single node. I think as you were mentioning, single node makes life so much simpler. Like so much of the coordination. I was just talking last night actually to a former coworker, who kind of has these. He had these amazing designs for shuffle and for kind of making helping queries scale out and distribute it in a distributed way. And he's like, he had this design for like the optimal shuffle, by reducing the number of RPCs to, optimizing the number of RPCs rather than optimizing for data movement. And pretty interesting stuff, but also like, if you're in a single machine, you just, that stuff just gets so much easier and so much faster. I mean, you can just like, if you've got a hash table, you just share that hash table. Like you don't have to, copy it around, broadcast it around, deal with retries, deal with failures, deal with like spilling, like it's just, you just share it. And yes, there's complications introduced by, in larger machines with NUMA and all that, but those are things you can work around.
So you mentioned Databricks, Snowflake, the benchmark war they were having. So 30 terabytes was the database size. That's pretty feasible on a single node too, right? I mean, even with today's technology, I can do 30 terabytes. Is that preposterous or is that doable?
I think that's doable. I mean, I think you're going to need a pretty hefty machine, but I think especially if you consider modern column stores are going to get pretty good compression on that. The actual data sizes on that might actually be smaller. Like I think you can likely do that on a single node. I don't know I don't know if anybody's tried that outside of like, they may be in like some big, HPC environments. But it certainly seems like you could do that, at least reasonably well, with a single node.
So another design pattern which we see very popular amongst customers, and again, I give some credit to Snowflake, but it's the fact that they're just simplicity. With software as a service, there's not much to install, and now more and more databases are going serverless. So you got SaaS serverless, you got a multi-tenant architecture. In your vision of developing a new product, how do you see these concepts play a role?
So serverless is definitely very important, and
Okay.
Everybody sort of is chasing serverless, and I think one of the things that is sort of I see kind of as a flip side of serverless is really sort of like elastic scaling up and scaling down. I think actually one of the underappreciated is everybody thinks about scaling up. How do I scale it up when things grow? But I think that also the thing that's really important is to scale down, and to scale down to effectively zero. Because if you're just somebody who wants to kick the tires and you want to see how well this works, you should be able to for a couple dollars a month, be able to start using something. And then as your data size and your workload size grows, and maybe you go from test into production, you should be able to just sort of scale up with a single knob, and make it very simple. And I think you mentioned simplicity is I think for the kind of the smaller customers, the smaller users, or the individual analysts, the kind of the ergonomics are important, and the ergonomics of getting started. I think this is another area where we kind of see things being underserved, or the potential for being underserved by some of the larger vendors. And I think one of the reasons is everybody is chasing the same enterprise, giant enterprise customers, and absolutely that's where, it makes sense. That's where the majority of the money is. And for these people that already have these large data systems. But the problem is they have all these requirements. They're like, okay, well, I want to do DR between London and Hong Kong, and I want to do and I have these security requirements, and this is how we do data masking and tokenization in the on-prem, and I want it to work exactly the same way when I'm in the cloud. And so much of then the roadmap gets taken up by kind of chasing these customers. And these are not easy things to build. Like disaster recovery that spans the globe is incredibly difficult. And I think the way teams tend to justify it is like, okay, we're just going to do these three things that are being asked for, and then the next then we're going to be able to get 25 more customers because this is going to solve everybody else's problem. And it turns out it doesn't. It turns out then once you solve those three problems, and then there's another 30, and it's all important, it's all valuable. But the thing is that when you're doing that, like the economic buyer, the person that you're selling to, is not the user. And I think, so far, most of these vendors have done a pretty decent job of, still actually catering to the end user. But I think there's a trend in enterprise software, and I think we call it the workday problem, where, something that is great for the people, the C-levels that you're selling to, there's no incentive to make it work really well for the end user and the people that are actually stuck with using the product. And I think there's some opportunity to sort of get gain customers with who have smaller workloads, who have smaller data, and then kind of have that spread throughout an organization. And and I think each one should be able to sort of in a small budget be able to use it. Because the other kind of one of the other things that I strongly believe is that all big data starts out as small data. And when you focus on the giant customers who already have big data, you kind of you miss out on how that journey happens from small to big. But and I think it's people don't disbelieve that that's true, but I think also they're not paying attention to how that happens. Like it's by focusing on the customers that already have the giant requirements and the giant data, the people that are, the smaller users who are going to grow into the bigger users. I was trying to, think of customers that in BigQuery that were, those small customers that grew into giant users. And one big example was Snap. They got their early start on Google Cloud, and they were a very early BigQuery user, and their usage was very small in the beginning, and I don't think they paid a whole lot of money, and then they grew incredibly quickly, and then they became one of the largest customers in Google Cloud. That's no secret. And then they become a massive user of BigQuery. And so I think if you can, if you focus on getting users in when their data sizes are small, then workloads increase really quickly. And that's something we also noticed in BigQuery, is just that the way A, data grows, and B, like, if you get data grows within a workload. I mean, because if you think about data being collected over time, you accrete more data over time. But then you can also, realize, hey, this works well for this workload. You tell your friends, you tell your coworkers, and like, hey, you built this great dashboard. How can I use this too? And then so it's not just a linear increase in size, but it's also sort of a quadratic increase in size as you spread it towards, throughout the organization.
Yeah. So there's 2 points I want to make here. First of all, I think serverless is great. I love serverless, but serverless serves, ad hoc queries. You want to run something, very efficient use, you pay for the consumption, and then you get results back. But a lot of data warehouses do pretty heavy duty ETL processing, which is not really a serverless function. So you need to elastically scale. Now, the problem with that elastic scale is that that elastic scale, we just get enamored by it, but we have to think about how fast did it scale up? Did it scale down or in? Let's say I have 16 nodes and I just need a little bit more. Am I going to the next t-shirt size, which is 32 nodes? Now I've scaled up, but my cost has gone up. Then what happens to my cache? What region did it scale in? I mean, the scaling is a very detailed, the more you look into it, the more you find out it's very nuanced. So in your view, do you support both serverless and elastic scale?
So I think that, the serverless and scaling are intricately tied. And I think everybody wants this magic thing where, it's both predictable spend and can be scaled, infinitely, immediately, as needed. And the problem is those two things actually work against each other. And so in BigQuery, we had, one of the nice things about BigQuery is, you can scale from 0 to very, very large and very quickly. And then, and the billing model reflects that.
How fast do you scale? Because, your load's gone up, and if it's going to take you 5 minutes, and if you have to bring your system down to scale, and you cannot do that, it has to be online and instant.
Yes. But the other thing is, if you're scaling it instantly, I mean, if the company is, or if the vendor is going to give you more resources to scale instantly, then that's going to come with a cost. And sometimes people are surprised by that cost. And so that was, every month or two, there would be somebody, a student who runs some sort of script in BigQuery and ran up a massive bill. I think there was one case of somebody running up a 7-figure bill, in a couple of days. And then I think they're still working in the salt mines at Google. BigQuery has been good for helping to populate the Google salt mining community. No, I mean, we would always refund those users when it happened, but I think there were a lot of people that got really terrified when they saw their their accidental bill. But that's the sort of the flip side of true elastic scale to the size that you need, is that also means that, like, okay, we'll give you what you need, but we're going to also charge you for that. And so I think you need to also make sure that there's the right controls, so that you don't scale up immediately. The other kind of side is you sort of have fixed pay for resources, and that is and that's sort of the more old school, more inflexible model. And I think you can have sort of a blend where you kind of allow elastic scaling, but you set some sort of guidelines. And especially when you mentioned caching, most modern analytics systems have some sort of state, some sort of caching that happens. I think BigQuery is pretty unique in that it has the underlying storage system is fast enough that it doesn't need to have any caching. It doesn't need to have any state. Of course, the underlying storage system does have a bunch of interesting caches, but how do you deal with state management when you're scaling up and scaling down? Because you do have to populate those if you're increasing, if you're going from 1 node to 2 nodes to 12 nodes, you have to you're going to have to hydrate those caches. And I think this is also an example where single node can be interesting, because if you scale up within basically if you have a resource governance within a single node, if you scale up within that single node, well, the data is already pre-cached. Which I think gets to the other interesting point, which is, or salient point, I don't know if it's interesting, is that I think if you're going to have an efficient system that scales down to 0, it's got to be multi-tenant. Like, I don't think there's any other way to build it, because if you have to, like, I think so many people, what they're doing is their cloud service, they're taking a database or a data management system or data analytics system, and they're running it in the cloud. And the way they run it in the cloud is multi-single tenant. Each one of their customers gets a virtual machine or container, Kubernetes container instance. Maybe it's a cluster, maybe it's a single node. And from a Kubernetes management perspective, it sort of makes sense. Okay, you spin one up, and then you kind of, Kubernetes does this thing, finds the resources, spins it up, boots the VMs, et cetera. But that takes minutes. That takes a long time. And I think that's, unsatisfying for users. So, okay, you have some hot standby sitting around. And so you can use those. And you can hack around the problem that way. But on the other hand, like, those are going to be expensive. Like, that's just, like, one of the things that I was saying is I believe that scale down is important. So, being able to spend just a couple dollars a month, and that's if you're using it, like, not just like, sitting it, okay, I use it for 2 hours and then I shut it down. But, I think you should be able to use it pretty consistently for a small amount. And that's almost impossible with, when you have a, Kubernetes based system where you're spinning up VMs, even a small VM. And so I think that one of the keys is multi-tenancy and sort of being able to run multiple customers on the same hardware. And I think, Snowflake doesn't advertise it too much, because they kind of don't like people to realize that they're sharing resources, but Snowflake does a lot of multi-tenancy. And I think even they don't do a great job of scaling down. BigQuery is, of course, a giant multi-tenant system. When I left, we had something like 3 million cores devoted to BigQuery. And, pretty much all of those cores are running, in this, they're finally sliced up by, pretty much on the per millisecond basis to basically give these slices of resources to people. But so that was a giant multi-tenant system. And one of the things that's actually been surprising to me is how few people are actually doing multi-tenancy, and, like, because, how many of these data systems are are just following the single tenant model. And I think, Cockroach is a good example of like, that's, how they built their, their always free Cockroach version is they figured out a way to make a multi-tenant system that was very, very resource efficient, because like if you're a startup and you're running an always free tier, if you're going to if that always free tier involves running a Kubernetes like instance somewhere, a VM or a container, that's going to be expensive, and that's going to be a major source of cost drain. But if you can make it multi-tenant and you can shrink it down to zero, then your costs can go to zero, and you can give actually a much more generous free tier. I believe also Mongo does something similar with their free tier. Although I think the other thing that if I was going to poke at those a little bit, is that I think it's like, well, do you want multi-tenant or do you want sort of the real thing? And I think in order to kind of do it well, like it's just got to there shouldn't be this jump. It should be, there's, the multi-tenant thing, can, you should be able to scale with the multi-tenant system and get good isolation and good performance guarantees. Perhaps at the larger sizes, you say, okay, I'm using this massive thing, and I want you to reserve my own, instances. Like somebody's writing you a large check, you can always, do those kinds of things for them. But it's, it's nice when that's sort of the exception, for the person that wants to just negotiate something with their, CFO. Hey, I need this, $25,000 a month for X service. You write that check, and then you get the hardware, and you're not quite as interested or worried about the scaling.
So Jordan, the whole scaling, multi-tenant, serverless, we can talk, a whole episode on that, because I'm also thinking when we talk scaling, we talk about compute scaling, but then there's storage. Scaling down storage is like, you just can't do it. You have to like rebuild it, export, and then there's a network connection scaling, and so there's a lot of topics. I would love to change the discussion into developer experience, which I want to pick your mind on. You've done a lot of work on WebAssembly, and what's the role of WASM, if you can even explain. But before we go there, I have a burning question. You mentioned that the working set is typically much smaller than the overall size of the data warehouse. How about joining tables? And what's a typical 10, 20, 30, 40 tables? Because I know Teradata killed it in its early days because they could just join tables very easily. But some of the newer ones are built in a way that can they join? Absolutely. But your build will be huge. So what do you see in terms of data modeling, semantic modeling, joining like tables? What's your view on what's typically the case and how to do it best?
I do think that everybody, everybody says like, oh, well, the world is changing, everything's going to be denormalized, and everything is, so you can do basically the pre-joins. But I also think that the Kimball model, the fact and dimension tables, and is for analytics is kind of here to stay, just because that's the way people's brain works, and the way it's just sort of like, okay, you have the products catalog over here, and then you have your orders and your line items, and I think that's just you can mix those together, but it at some degree it's sort of unnatural, and so I think that it's important to be able to do joins and to do kind of high velocity joins. And the thing so every data system, they want to say, well, you just throw your data in and it just works, and it's just fast. The problem is that unless you pay attention to how it's stored, it's not going to be fast, particularly when you throw joins in the mix, particularly when if you have dimension tables that are not tiny, and you can't just sort of broadcast those around, and so you end up at some point you have to sort of you push that requirement back on the user and say the user has to specify, okay, this is how I want the data partitioned, this is how I want the data indexed, and this is, and then you end up needing a DBA. The initial promise of Dremel, which is the query engine underlying BigQuery, was that we can make a table scan fast. You don't need indexes, you don't need all these, you don't need partitioning, you don't need all these things that are typically associated with databases. But the one thing that it wasn't able to do is make it inexpensive. It's like, yes, we can make it fast. We can, like I think the original paper is, we can scan a terabyte in a second. And, that was, 15 years ago. I think they can do more now. But in order to do so, it's going to take, thousands of cores to do that, and terabytes of memory. And so, a lot of the last 10 years of BigQuery has been, okay, well, yes, we can scan a terabyte of data that quickly, but we're wasting a lot of resources when, we're looking to get a needle in a haystack. And if you have to read that, through the whole haystack, why don't we introduce partitioning, introduce, different ways of doing pruning that will allow us to sort of jump right to the thing that we are looking for, and ended up, sort of recreating a lot of sort of what is typically found in databases and data analytics systems, but at the same time making it more complex. And you mentioned the developer experience and tying it to kind of a semantic model. And I think there's something interesting here, which is if you can define your semantic model, then you have a map into how the data is being used. And so one of the things that makes automatically designing schemas, designing indexes, designing partitioning, designing the physical layout of your data. One of the things that makes it more difficult is you don't know the questions that are going to be asked ahead of time, and you want to be able to support, truly exploratory analysis. But when you're dealing with applications and to a large extent, people that are doing dashboarding and BI, the types of questions that get asked are really kind of narrowly defined, and they're defined and the way that they're defined is the data model or the semantic model or the metrics layer, I think is what all the cool kids are calling it these days. It constrains the types of questions that are being asked. And I think there's an opportunity here for using that model to infer the physical storage of the data. So because basically if you say, hey, these are the tables that I joined, and these how I join them, and basically these are the aggregations I'm going to do, and you can use that to basically say, okay, well, I need to make those fast, and so that's a solvable problem. Is like, how do I make this query fast? Is something that is a solvable problem, and an automatic, okay, well, in order to do this, I will need an index on this column, or I will need, basically there's a relationship between these two things here. I'm going to need to be able to join these. Maybe I need to sort of pre-join. Maybe I need to sort of to shuffle this in a different way. Maybe I need to partition this in a certain way. And so I think there's a bunch of interesting things that can be done on an automatic, from an automatic perspective, if you have this well-defined semantic models, well-defined metrics layer. And I think sometimes people try to approximate it by saying, well, all right, what we're going to do is we're going to use machine learning to figure out what the joins are, and then we're going to recommend to you what indexes you want. And I think one of the problems with that is it's sort of this action at a distance, this magic where you say, I'm going to magically, make your queries fast. But the problem with magic is, like, when magic doesn't work, people have no idea how to fix it. They have no idea what went wrong, and they have no idea when it's going to kick in again. And so I think that the nice thing about using the semantic model to inform that is you don't need any magic. Once you define that, you can basically start building building indexes that you need.
So, and let's talk about WASM, because we're getting to the end. First of all, what's the magic power of WASM? Why would one need it? and how would it show up in your product?
So WASM is WebAssembly was originally designed to be able to run arbitrary code in the browser, and it's pretty interesting from that. And I think it is kind of expanded into, people are running it on the server side, people are running it in the database, people are kind of using it for, and I think to me, like, the best technologies are technologies where, people find interesting ways to use it that go way beyond sort of what the creators are intended. And I think WASM is a fantastic example of that. So it's a secure runtime environment that can run in the browser, can run arbitrary code in the browser in a secure way and in a performant way. Like, it actually can execute things at near native speeds. There are some like limitations and drawbacks, and like, I think the data specification has sort of yet to be fully fleshed out. Like, how do you get data in? And I think if you're going to be doing database stuff, you need, that's very important, is sort of what's the pipeline in. What does that look like? At Single Store, we were working on WASM, basically embedding WASM within the database, so you could kind of call out to you could execute arbitrary code in the database, and there's lots of kind of cool things you can do with that. But one of the things that has never existed before, and as maybe a teaser, one of the databases that I find quite interesting is DuckDB. DuckDB is this, they like to call it SQLite for analytics, and DuckDB, there's a researcher at Carnegie Mellon who has professor who has gotten DuckDB to run in WASM, and which is kind of super interesting, because I think one of the things that has always been a limitation is you don't have a database on the client side, and I think there's a bunch of places where that comes up. Like, one is security and encryption. The early days of BigQuery, there were some kind of research folks that were interested in homomorphic encryption, which is sort of like encryption where the database never has to store the unencrypted data. So you don't have to actually trust the database with your keys. You can do everything on the client side. And one of the reasons that sort of broke down, one was the algorithms to do that were like incredibly expensive. But on the other hand, you needed a kind of a database on the client side to be able to sort of rip the queries apart and do this sort of like the ciphertext versus the clear text, and kind of do the munging that you needed. But if you can run the database on the client side, you run the database in WASM, you can do that munging in a pretty clear and transparent way to the user. And that's sort of one example of how having data on the client side, or having a database on the client side is interesting. And other examples are being able to sort of do some client side analytics, or basically do analytics where you can actually operate in a disconnected mode. You can sort of, let's say you have like your backend system has all of the data for all of the users, but the client side, you can actually cache the data for just that user, and then they can actually run queries against their own data, and locally, and the things that maybe have to access older data or other things can run then in the cloud. So I think there's a bunch of just so interesting things that can be explored from this. And again, I think one of the things that is interesting about technologies, or I think when you have technological leaps, is when you have something that has been a barrier and then all of a sudden some new technology arrives or some new way of thinking arrives, that barrier is then dropped, and then you can start thinking about what are all the different things, the implications of that. And I think WASM client-side databases are both technologies that can enable things that we haven't even thought of to become possible.
Wow. So we have a lot of things to look forward to, and this is a kind of the new way of thinking, the new generation of databases with these serverless small side, running even on the client side in a browser. uh, and then we haven't even touched upon the authentication model, the connectivity. I think there's a lot of interesting things that you're thinking. Maybe a minute or two on that.
Yeah, sure. So I think, just traditional applications are built as three-tier applications. You have the client, the server, and then the database. And that puts a lot of constraints on how you build those. And I think, Firebase was the first one that I saw that actually lets you do a two-tier system where the clients have direct access to the database. And I think there's some really interesting things you can do with two-tier systems. And when you think about serverless in the sort of the Lambda function side rather than serverless, meaning you have no server. So you can build applications with no backend if you have the database, that are running, Lambda functions and sort of event style programming, and the database then becomes directly accessible by the application, or the data analytics becomes directly, system becomes directly accessible from the client. And the key and the interesting things is how do you do that in a secure way, and can you do sort of attenuation, so you give keys that only give access to sort of pieces of the data. But that's probably a detailed discussion of that is beyond the time that we have left.
Yeah, but it's exciting to see the possibilities. Before we end this show, Jordan, you live in Seattle, correct?
Yes.
And so what are you most looking forward to for the rest of this year? Personally, work-wise, fun stuff, and what's on your mind?
So I'm a big rower. I like to row. I didn't row in college, and maybe that's the reason I still like it, because the people that did row in college are like, the sport is way too brutal to actually do for fun. But there's nothing lovelier than sort of being out on the water when the sun's coming up, and it just sometimes you get one good stroke in, and it's like all is right with the world. So I'm looking forward to actually getting back into sort of team rowing again, sort of now that I wouldn't say COVID is winding down, but people are able to do some of these things again, and sort of getting back to sort of some rowing and some racing should be fun.
Wow, very nice. When it's not raining in Seattle.
Right? It doesn't really rain here. Liquid sunshine.
That's good. That's great. Thank you so much for joining this episode. It was, as always, quite eye-opening listening to what's coming down the pike. Reminds me of Pike Place when I think of Seattle. But thank you so much. Anything you would like to add before we wrap up?
No, thank you. Just thank you for the opportunity to chat with you. It's always fun. I love to talk about this stuff. And yeah, thanks.
Great. Thank you so much. Thanks, everyone.